Hi, I'm Rowan from Vantage Admissions, a specialist tutor for university admissions tests and a former STEP examiner. Now, this video is going to be a bit different from our usual content. I'm going to be taking, unseen, Step 2 2025 in mock conditions. So this is purely for entertainment purposes, not educational purposes. I'm not going to be careful with my exam technique. I'm not going in with any particular strategy. We're just going to go in and see how it goes. And then hopefully you can learn from my mistakes. So this is going to be quite a long video. We're going to break the video down into chapters. So there's going to be a very long section after this, the raw footage of me working through the paper. The next section will be me going through the mock, having had it marked by a colleague who has also been a STEP examiner, and then we'll have some final reflections at the end. Wish me luck, and I hope you enjoy. Well, I'm fairly nervous. It's been quite a while since I've done one of these properly timed. Hopefully it will go okay. So I'm going to have the questions on my computer screen because unfortunately my printer's broken. I have a stopwatch here, which I'm going to keep an eye on. I guess we can begin. So opening the paper now, everybody knows, unless you have a very good reason for doing otherwise, you should always begin with question 1. This question doesn't look too bad, so I think I will do that here. Conceptually, it looks very straightforward. I mean, this min function, just a piecewise function, I assume they're going to pummel us in terms of algebraic intensity by making us do this. So best to do it when I'm fresh. So let's start with question 1. So first of all, we need to sketch min x squared 2x. I might as well express it explicitly as a piecewise function first. So let's just solve the inequality. So x squared is less than or equal to 2x when x squared minus 2x is less than or equal to 0, when x minus 2 is less than or equal to 0. And that is true when x is between 0 and 2. So that means that the function min x squared 2x, I'm sure the examiner will let me off for not doing a capital M, is going to be, well, I've got several cases. I've got when x is less than 0, I've got when x is greater than 2, and I've also got when x is between 2 and 0, well, 0 and 2. In this case, by my inequality work here, x squared is the smaller of the two, and in the other cases which arise, it's actually going to be 2x which wins. Okay, so that should be enough, I think, to draw the graph. Okay, so note as well that it's a continuous function, so I don't need to be overly careful about where I put the or equal to, because at the value when a and b match, they're the same, so it doesn't matter which one I use as the minimum. So at x equals 0, I'm sketching 2x, but that is actually at 0. And then I've got the line y equals 2x up to that point. So that's just going to be a line of negative gradient, or positive gradient rather, gradient plus 2. So that bit there is just y equals 2x. Then I get the quadratic curve up to x equals 2. So by x equals 2, y should be up at 4. So I'll have it do something like that. Now, I'm trying to think about what happens to the gradient at the changeover point in case the mark scheme is fussy. So I might even write some workings here. So at the changeover, which is x equals 2, well, the derivative of x squared evaluated at x equals 2 is 2x evaluated at x equals 2, which is 4, which is bigger than 2. So I know that the graph should actually become flatter at that point, and therefore I'm going to slightly modify how I've drawn it so that it looks a little bit steeper by there. So that's meant to be a gradient of about 4, and then it flattens again, and that should obviously be parallel to that stretch. So that there is the point 2 4. And because my graph is not completely convincing, I'm going to include a written remark for the marker, which is that this line is flatter than the curve at the changeover. So could have drawn that better, but I think that should suffice. Right, now on to part 2. So in part 2, we have to solve an equation. So 2 min x squared 2x equals 5x minus 3. Well, I can just turn the equation piecewise using precisely my work here, because it's the same min function. And then I can just solve the equation on each portion of the domain and discard any solutions which are then false because they're on the wrong bit of domain. So that shouldn't be too bad. So, okay, well, I know what 2 min x squared 2x is. It is just exactly what I wrote for min x squared 2x, except that everybody gets doubled. So I get this, I get this, 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 and then this. How are we doing for time? Under 5 minutes. Okay. So far, so good. Now I can express the equation piecewise. I'm going to tell the reader that I'm doing that so that they don't just see a bunch of equations with no explanation. So for the x less than 0 case, my equation reads 4x equals 5x minus 3. On 2, and sorry, that should say x, not 2x, not x squared. And then from 0 to 2, I've got 2x squared equals 5x minus 3. And then for x greater, that should say greater than 2. Right, and then for x greater than 2, we've got 4x equals 5x minus 3. Did I write those other domains wrong? No, they were all fine. Okay, so I'll denote these 1, 2, 3, just so that it's easier for me to now work case-wise. So for case 1, I mean, that equation's very easy to solve. I get x equals 3, but I discard as 3 is not less than 0. So because I've taken the equation piecewise, I'm having to discard things that are on the wrong bit of domain, and I've made sure to actually state that so the reader knows I'm checking. This one, I guess, is slightly more non-trivial. So I get 2, well, let's make a bit of space. 2x squared minus 5x plus 3 is 0. I think we can probably factorize that without appealing to the quadratic formula. If I use a minus 3 and a minus 1, that gives me minus 2x, minus 3x makes minus 5x, and then I get my plus 3. Good. So that is solved when x equals 3 over 2 or when x is 1. And I keep both as they are in the interval 0 to 2. So even though what I'm doing is not discarding them, I still need to make sure I tell the reader that I've actually done the check. And I'll circle these so I know in a minute to come back and collect them. And then case 3 is actually the same equation as case 1. It's just on a different domain. So that gives me x equals 3. And then this time I keep as 3 is bigger than 2. Okay, so what are my solutions in total? Well, I've got 1, 3 over 2, and 3. I think that's okay. Okay, and part 3, it's pretty obvious what this is going to entail, but it's going to be really painful because we've now got 2 separate min functions. So I'm going to have to split each of them piecewise, which is kind of annoying. But then I have to split my equation up according to when either one of them changes. So this is going to be irritating. That being said, we're only around 7 minutes in, so we've got time to take it slowly. Let's consider each function separately first. So minimum x squared 2x. Well, that's actually one I've already done. So I'll just recollect what I said that was already. So I had an x less than 0, x between 0 and 2, and an x bigger than 2. And this does not have the factor of 2 in front, so this time it's just 2x, x squared, 2x. And then as for the other one, well, when is x cubed less than or equal to 4x? Well, that's equivalent to x cubed minus 4x less than or equal to 0. That's equivalent to x squared minus 4 less than or equal to 0. That's equivalent to x minus 2, x plus 2 less than or equal to 0. Both for the examiner's satisfaction and so that I don't mess up, I'm going to draw a quick plot of such a cubic. So it's a positive cubic that cuts at those points. So I can see that this is true when x is less than or equal to minus 2, or when x is between 0 and 2. Yeah, okay. So that means that function min x cubed 4x is equal to, well, when x is less than or equal to 2, my inequality is obeyed, so it's the x cubed that wins. And then from 2 up to 0, my inequality is not obeyed, so the 4x wins. And then from 0 up to 2, my inequality is obeyed, so the x cubed wins again. And then for x greater than 2, my inequality is disobeyed, so 4x wins. So I've got 4 cases there. And now I'm going to have to split my equation as well. So the other piecewise function split at 0 and 2. At least this guy also does changing over at 0 and 2. So I'm not going to have even more cases from them having different split points. Let's just write the equation piecewise and hope that it's manageable. So what cases will I actually have? Oh, and that should say minus 2, not 2. That should say minus 2. That was close. So I've got the case when x is less than or equal to minus 2. I need to split into a new case at minus 2 because the second min function changes, even though the first one doesn't. And then I need to split at 0 because they both change. And then I also need to split at 2 because actually they both change again. So maybe I'll write a quick note to the examiner that I'm being careless with strictness of inequalities as the min function is continuous. So at the point where I'm changing over, it doesn't really matter which one I use because the whole point is the minimum of 2 numbers which are equal. It doesn't matter which one of the 2 numbers I take. So I don't need to worry that maybe I've been inconsistent with my or equal to's. That's completely harmless. So for x less than or equal to minus 2, I've got 2x and x cubed as the correct choices for the 2 functions. So I get 2x plus x cubed is equal to, I'll leave this as a general m for now, but we'll probably split into cases in a minute. Then when I cross minus 2, the 2x has still not changed because x is still negative, but the cubic does change. So now that becomes a 4x instead. Okay. Then when I cross 0, they both change. So now I've got the x squared from the quadratic and I'm back to x cubed from the cubic bit. And then finally, when I cross 2, they both change again. I've got 2x and I've got 4x. And I'll split these into cases to handle separately. So, okay, bit tedious, but now I've just got some really simple equations that I need to solve. And I guess I'll just do an m equals 2 and m equals 6 analysis completely separately. Let's signpost that for the reader. So, okay, for m equals 2, I will collect what my equations read, but I will simplify them slightly. So for the first case, that is now a 2x, so the x is cancel, so I get just x cubed is 0. For the next case, I get well, 4x equals 0. For the next case, I get x cubed plus x squared minus 2x is 0. That looks a bit horrible, but even though it's a cubic, at least I can pull off an x. And then for x greater than 2, I've got, well, again, 4x equals 0. Right, let's take the cases. So case 1 tells me x equals 0, but I'm going to discard it as 0 is not less than or equal to minus 2. We might get an x equals 0 solution again later and then get to keep it from that domain, but not from this one. The second case tells me that x equals 0, but I'm going to discard as it's not in the strict interval minus 2 to 0. So it almost is, but for this one I wrote it as strict, so I'm not going to allow that 0, although based on the fact we said that the strictness and non-strictness wouldn't make a difference, I'm expecting that x equals 0 is going to reappear for case 3. And indeed it will, because if I pull out the x, that's obviously telling me I have a factor of, well, a solution of x equals 0. So I get that. And then I can factorize that quadratic, x plus 2x minus 1. So I get x equals 0, 1, and minus 2. But I had to be on the interval 0 to 2, so I discard minus 2, as it's not in 0 to 2. So I mustn't just do this mentally. I have to actually tell the examiner I've checked, because there might well be marks allocated. And then finally, case 4 tells me x is 0. Well, in this case, I'm going to discard as 0 is not greater than 2. Okay, so what have I got overall? So for case 1, I got nothing that I didn't discard. For case 2, I got nothing that I didn't discard. For case 3, I got 0 and 1. And then I got nothing else for case 4. So it looks like the only solutions we find are 0 and 1. Which feels a bit funny, but maybe that is okay. Yeah, I think that's fine. Let's go to the next case. If we have time at the end and I have the energy, perhaps I'll come back and check. How are we doing for time? 16 minutes. Okay, that's all right. So what do the equations read for m equals 6? I mean, I'm expecting something interesting to happen. They're not going to get me to do the same thing twice, just with different numbers. There has to be something interesting. So what does this guy become? This guy becomes x cubed minus 4x equals 0. What does case 2 become? So here's the interesting thing. Case 2 trivializes. The x's perfectly cancel. So that's going to tell me that everything on that domain is a solution, which is quite nice. And then for case 3, I've got, well, the worst of all, right? X cubed plus x squared minus 6x is 0. But I'm not that worried because I can factor off an x. And once I factor off an x, I've got a quadratic. And then I've got case 4, which also trivializes to 0 equals 0. Okay, very good. That should say up to 2. That should say greater than 2. Let's take the cases. So case 1 solves to give me x squared minus 4 is 0. So x minus 2, x plus 2 is 0. So x equals 0 to minus 2. I keep minus 2 only as I need x less than or equal to minus 2. Okay. Case 2 is trivial. So that means that all x between minus 2 and 0 are good. Nothing wrong with that. An equation can have a solution that's an interval, not just isolated values. And this is quite a common finding when it comes to piecewise functions. I am relieved to see that something interesting is happening, because otherwise I would have thought it doesn't really make sense from the perspective of the question setter. Right, case 3, I'll pull out an x. x squared plus x minus 6 is 0. I will factorize x plus 3, x minus 2. is 0. So x can be 0, 2, or minus 3. But I keep 0 and 2 only as I'm looking at the 0 to 2 case. And then finally, case 4 is trivially true, so that means that all x greater than 2 is a solution. So let's collect then. I've got minus 2, and I've also got minus 2 to 0, and I've also got 0. So that means that overall, anything from minus 2 to 0 inclusive is a solution. And then I've also got 2 and everything greater than 2. So that means x greater than or equal to 2 is also a solution. So I'm feeling pretty good about that because there's been a genuinely different finding in each part. So I'm not suspicious that it all seemed a bit too trivial. Okay, 19 minutes. Should be finishing quite soon. We've still got part 4 to do. So I need to show that something is a local maximum of a given function. Well, it's served us very well so far to just blap everything out piecewise. Let's do the same here. And also, did I remember to write part 3? Yes. So I must remember to tell the reader which part I'm doing so they know where to look. So part 4, well, when is it the case that x squared is less than or equal to x cubed? Well, that's equivalent to x squared 1 minus x less than or equal to 0. Again, for my sanity and the examiner's, let me actually draw this. It's a negative cubic this time. It touches at 0. It cuts at 1. So something like that. So that is true when x is 0, when x is, and also when x is greater than or equal to 1. But I'm going to be really lazy, and I'm going to ignore this, as at x equals 0, the two things agree anyway, so it actually doesn't matter who I pick. So while I could, if I wanted to, make the function change between x squared and x cubed for that one point x equals 0 and then change back, that would be stupid and wasteful because actually the functions agree at that point anyway. So I'll be lazy and I'll ignore that changeover point. So what then is the minimum function of x squared and x cubed? Well, it's only got 2 cases because it only has to change at 1. So I've got when x is at least 1, the x squared is smaller. So by the satisfaction of my inequality, I'll use x squared. And when x is less than 1, I will use x cubed. And it doesn't matter that I meant to use x squared at x equals 0 on that domain because they agree. Okay, so what is my function then? Let's give it a name. So if I call fx 2 min x squared x cubed minus 5x, what does it read? Well, it reads 2x cubed minus 5x and 2x squared minus 5x when x less than 1 and x at least 1 respectively. I think that's correct. I've remembered my double. Okay, so I want to look at turning points, presumably if it says maximum. So f dash x is 6x squared minus 5 and 4x minus 5. Oh dear. Well, neither of those are going to be solved at x equals 1. So either I've made an algebra mistake, or there is more going on to this part than meets the eye. Now, I don't think I've made an algebra mistake. The only thing that could have gone wrong, really, is I could have somehow switched around the x cubed and the x squared at some point. Or I could have forgotten to double, but I didn't. The only thing messing up the min piecewise could have done is switched around when I have one case or the other. But clearly neither of them are going to be 0 at x is 1. So I don't think I've made a mistake. I think there's something else going on here. So there is not a turning point at x equals 1. So the reader knows that I'm not stupid. I've realized that this is not giving me what I want, but I'm going to try and think about why else there might be a local maximum. Well, what else is interesting about x equals 1? Well, it's the changeover point. It's when the function changes from one form to the other. And although we said earlier that the min function is continuous, it doesn't jump in value, we also noticed in part 1 that it's not smooth, right? Because we saw there an example where the gradient jumped. So I'm kind of wondering if I end up with something like that, where I have a kind of pointy cusp where it goes up and then back down. Let's evaluate the derivative in each of the two cases. So as x approaches 1 from the left, the derivative, well, I meant to use that formula, so it tends to 1. But as it tends to 1 from the right, I meant to use that formula. Here we go. And so it tends to -1. So that means it was increasing until x equals 1, decreasing from x equals 1, so has a local max. And just to really impress the marker, I'm going to say it's a cusp and draw a little picture of what I mean. So it's like it almost has a little point like that. So I've shown there is a maximum at x equals 1. They wanted to know the y-coordinate as well. So further, note the y-coordinate is, well, I'll just use the formula, 4 times 1 minus 5, which is, that looks, oh no, I've plugged it into the derivative. That's why that was coming out wrong. I have to go back up. Plug it into that. 2 minus 5, which is -3. So I have a local max at 1 minus 3. Okay. They want me to also find the other 3 local maxima and minima. Well, there's not going to be anything else that's cuspy like this because of the fact that there's only one changeover point. So I guess it has to be the case that the other min and max must come from when the derivative is actually 0. So other, let's say TPs, well, what's the equation I'm solving? I'm solving 6x squared minus 5x is equal to 0, or I'm solving 4x minus 5 is at least 1. Sorry, it's equal to 0 rather. That's the domain I was reading there. X at least 1, x less than 1. Okay, so now what? Well, I can solve these equations. So case 1 gives me looks like it's going to give me too many. Have I copied that wrong? Yes, I have. It's 6x squared minus 5. So that gives me that x is plus or minus the square root of 5/6. And I keep both. As they're both on x less than 1. And then the second case gives me x equals 5/4, and I'm going to keep it as x is at least 1. Right, so I found the x coordinates. They have said to find the 3 other maxima and minima. So I suppose I had better work out the y coordinates as well. So what's my actual function again? So for case 1, I'm on less than 1. So at x equals square root 5 over 6, what is y? 28 minutes. Let's make this fast. So x less than 1, I've got 2x cubed. So the cubed just gives me a 5 over 6, and then I get another one. 5 over 6. And then that's minus 5x. Minus 5 root 5 over 6, which is, well, is that right? 5 root 5 over 6. That looks fine to me. So I've got, if I factor off a root 5 over 6, I've got 5/3 of them minus 5 of them. But what is 5? 5 is 15/3. So I get minus 10/3 root 5 over 6. Okay, awesome. F is clearly an odd function on that portion of the domain at least, so I don't need to do any work for the other one. So by oddness, at x equals minus root 5 over 6, we're going to have 10 over, and sorry, that should say 3, not 5, 10 over 3 root 5 over 6. So I've got two of my turning points. I've got root 5, 6 minus 10 over 3 root 5, 6. I've got minus root 5, 6, 10/3 root 5 by 6. And then the last one's the easiest, just plugging in x equals 5 over 4 to the other. So we've gone slightly over the 30 minutes here, but I'm not too worried because I did say from the start this one was clearly going to be a slog. I'm hoping we can make up the time on some other ones. So for x equals 5 over 4, well, 2x, I'm using this portion of the domain. So I've got 2 times 25 over 16 minus 5x, and 5x is 25 over 4. So 25/8 minus 25/4, which is minus 25/8, I think. Yeah, so my other one is at 5/4 minus 25/8. Might as well now try and draw a quick sketch. Hopefully that won't take more than a couple of minutes, and then we'll be ready to move on to another problem. Okay, so what's going on? I've got... Where did I write the function? So I've got a cubic type shape to the left of 1. And I've got my turning points. Well, I've got 1, which is at root 5 over 6, which is a little bit less than 1. And it's got a negative... Okay, I'm going to have to redo my x-axis to make a bit more space. So if I put 1 here, I've got a x coordinate slightly less and a negative y coordinate. So I'll mark down here the turning point root 5 over 6 minus 10/3 root 5 over 6. That's a turning point. And from the overall shape, I mean, I know that for x less than 1, I've got actually a positive cubic, so I know it has to end up going down. Therefore, that must be a maximum. And I know that the y-intercept, which I better mark on, is at 0. What? That doesn't make much sense. Where did I write the function? Here's what I've done wrong. I'm neglecting that, of course, there is a negative turning point over here, which has a positive y-intercept. Sorry, so we've got that one there. There we go. Which is at minus root 5 over 6, 10/3. That's a maximum. I know I pass through the origin. I know I end up going down. because I've got a positive cubic, so it must end up for large negative x going down. I'm not going to try and mark on the other x-intercepts, I guess, because they're not easy to see. We might revisit that in a minute. I come down here, I cross the origin. I have another turning point, which is like the mirror image. So that's here at root 5 over 6, 10/3. That's got to be a minimum by the overall shape of a cubic. So I'm going to write that down. This is min by cubic shape. Then I'm going up. At x equals 1, I have this funny cuspy point where my gradient was 1, and then it immediately changes to -1. And then I've got my other turning point here. Now, the only thing I need to decide is whether 25/8 or 10/3 is, and that should be a minus there, whether 10/3 or 25/8 is the bigger number. So is that obvious? Well, 10/3 is what? It's 3 1/3. 25/8 is 3 1/8. So 10/3 is a bigger negative number, so it's not going to be as far down. Then I've got my other turning point at 5/4, 25/8, and then I zip off. And I think that's a completed graph. Can I mark on the other x-intercepts easily? If I can, I should do so. So actually, I think I can, right? Because I can factor off an x there, 2x minus 5. So that's going to be at 5 over 2. So I'll mark that on just in case. And then I guess I can solve for the other one as well, because I factor off an x and I get 2x squared minus 5. So the one that's on less than 1 is going to be at minus square root 5 over 2. So even though it's gone off the page, I'll just draw an annotation. And I'll say other x int at x equals minus root 5 over 2, then tends to negative infinity as x tends to negative infinity. If I had more time, I would redraw the graph carrying on a bit, but I think it's better with that annotation to just move on. So that's question 1, I think, done to completion. Question 2, okay, complex numbers. It doesn't look too bad. Normally question 2 is a bit nicer than the others. I'm just solving a bunch of equations. How bad can it be? So let's try and do question 2. So first of all, I need to deduce from this equation that z is either purely real or purely imaginary. Well, clearly z squared is, because I can make z squared the subject and it's something real minus a modulus. So, okay, z squared is a minus modulus z plus b. That means that z squared is real. Right, so if I write z is x plus iy, z squared is x squared minus y squared plus 2xyi. So real tells me that xy is 0, which tells me x is 0 or y is 0. But x is 0 implies pure imaginary, and y is 0 tells me that I've got something real, because they are the real and imaginary parts. Okay, that's part A done. Part B. Show that there are no pure imaginary roots. Well, why don't I suppose there is a pure imaginary root, plug it in, and hopefully get an equation which is inconsistent. So let's try z equals iy, which is pure imaginary. So if I do that, the equation reads minus y squared plus magnitude 5 over 2 plus iy equals 7 over 2. I can write the magnitude using Pythagoras. Minus y squared plus square root 25/4 plus y squared is 7 over 2. Okay, now I can do this, make the square root the subject, and then square both sides. I'm going to make a quick comment here, so I'm going to say squaring And I'm going to say no false solutions as both sides positive, because what can lead to false solutions from squaring is that things where you were out by a sign are now going to become solutions. But for two things that are manifestly positive, there's no prospect of being out by a sign. So I get 25/4 plus y squared equals y to the 4 plus 7y squared plus 49/4. So that reads y to the 4 plus 6y squared. They make -6, I believe. No, they don't. They make +6 when I bring it over like that. Equals 0. So this is a hidden quadratic in y squared. Now, even if this has solutions, doesn't necessarily mean y does, because if y squared has to be negative, that's no good. Y is real. What is the discriminant? The discriminant looks positive, so let's write down the full solution. So y squared is negative b plus or minus the square root of b squared, which is 36, minus 4ac over 2a, which is -6 plus or minus root 12, which is 2 root 3 over 2. But then, hang on a minute, as 2 root 3 is smaller than 6, because 2 root 3 squared is 12. Oh, no, that's not right. Did I mean 2 root 3? Oh, yeah, 2 root 3 squared, sorry, is 12, which is smaller than 36. So that means that both y squared solutions are negative, so that means no real y solutions. Right, the nerves and the fact we have to make up some lost time are getting the better of me. Let's stay calm. So that's part B completed. I think we've satisfactorily demonstrated there are no pure imaginary solutions. Part C, same basic idea. But now I'm going to plug in z is x. Okay, the modulus will be slightly harder because now I've not got a real imaginary, I've got pure real. I'll have to split into cases, but I'm prepared to do that, I think. So let's try z equals x in the reals. And actually, let's go up here and just mention that y is in the reals. Okay, so if I do that, then what does the equation become? The equation becomes x squared plus magnitude x plus 7 over 2 equals 5 over 2. Fine. Let's split this into cases. So a bit of a blast from the past with question 1. I've got a case when x is less than -7 over 2 and a case where x is at least 7 over 2 because of the fact that the modulus switches sign. So if x is less than -7 over 2, the argument of the modulus is negative, and I get this. There seems to be a funny trend sometimes where the same idea comes up in multiple questions. It's a bit different from min, but we're still just working piecewise. And then in this case, the argument of the modulus is positive. So I get that. So case 1 reads x squared minus x minus 6 is 0. So that factorizes to x minus 3, x plus 2 is 0, x is 3 or x is minus 2, but neither is less than -7 over 2, which is minus 3.5. So I have to discard both. Good. I wanted to discard them because I want there to be no real solutions. And then the second case is what does it simplify to? It simplifies to x squared plus x plus 1 equals 0. But the discriminant is 1 minus 4, which is negative, so we get no real solutions. So that means, overall, we see that no x work, and that means there are no real solutions, because a real solution would have been with an x. Okay, we're at 42 minutes. I feel we're making up our lost time in this problem. Maybe I'm speaking too soon. So part D, I'm given a range for B, and I need to show that this equation will have one purely imaginary and one purely real. Well, I can just take the two cases. I can plug in pure imaginary, plug in pure real, and hopefully this time I'll find a solution. Let's try pure imaginary first. I feel like that's easier because I don't get any piecewise work. So if z is iy, the equation becomes minus... I have a horrible feeling. Did I remember to put the minus on when I squared iy before? Yes, I did. Because I nearly forgot to then. Minus y squared plus magnitude iy plus b equals 1/2. So minus y squared plus square root y squared plus b squared is 1/2. So square root y squared plus b squared is y squared plus 1/2. Right, no false solutions on squaring as both positive. This is important because if squaring could introduce false solutions, then even having squared, I know that they might not be real solutions. They might be false. So, okay, if I square, I get y squared plus b squared is y to the 4 plus y squared plus 1/4. Marvellous. The y squared cancel. So y to the 4 is b squared minus 1/4, which is at least 0, because we did say that b was between 1/2 and 0. So this is positive as b, let's be really precise, b is between, 1/2 and 3/4, means that b squared is, half there, b squared is bigger than 1/4. So that means that y equals the 4th root of this is a real solution, right? I couldn't have had a 4th root of a negative because y is real, but I know that's positive, so all is good. Right, we've established the existence of a purely imaginary solution. Now let's try to do pure real. So pure real, z is x in the reals. So the equation becomes x squared plus magnitude x plus b equals 1/2. Just like before, I'm going to split into cases according to whether x is less than minus b or x is at least minus b. In the former case, my modulus is negative. So I get x squared minus x minus b is 1/2. In the latter case, I get x squared plus x plus b is 1/2. Well, I'm going to have to use the quadratic formula to solve these because they are, well, they're quadratics with an unknown coefficient. So this is going to be a bit awkward. Let's just take the cases. As long as I find that one of them works, we're good. So case 1, I get x is 1 plus or minus the square root of 1 plus 4b over 2. And I'll need to consider whether those are legitimate in a moment. And in the second case, I get x is minus 1 plus or minus square root of 1 minus... Oh, I haven't... How stupid of me. I haven't brought the half over. That's a bit of a blunder. Let's fix that. So that should be b plus 1/2. And that should be b minus 1/2. Right. Must stay calm and avoid these sorts of mistakes. So what does case 1 solve to give? X is 1 plus or minus the square root of b squared minus 4ac. So that's going to be plus 4b plus 2. So I get 3 plus 4b over 2. And for the second case, I get x is minus 1 plus or minus square root, 1 minus 4b minus minus still makes plus 2. So I think I get 3 minus 4b over 2. So note that all are real as b is between a half and 3/4, but I need to convince myself that 1 at least is on the correct domain. Well, for example, in this case, the only one that's going to be less than minus b is the negative solution. So I only need to find one solution, remember. So the negative solution of case 1 is 1 minus square root 3 plus 4b over 2. And I need this to be less than or equal to b minus b. I've said or equal to as it's continuous at the changeover. So equal to would be okay as well, because I could use either equation at the changeover point. So 1 minus square root 3 plus 4b over 2 less than or equal to minus b is equivalent to, better make it clear I'm using reversible logic, 1 minus square root 3 plus 4b less than or equal to minus 2b. That's equivalent to square root 3 plus 4b greater than or equal to 2b plus 1. That's equivalent to, well, squaring's a bit dodgy, because if I go the other way, in principle, I'm going to get moduluses, but I know that both sides are positive, so I could drop the moduluses. So this is reversible as both sides positive. Squaring, I get 3 plus 4b, at least 4b squared plus 4b plus 1. That cancels with that. So I get, as long as 4b squared is less than or equal to 2, as long as b squared is less than or equal to 1/2. But what did we say about b squared? Well, I know that b is between 1/2 and 3/4. So b squared is between 1/4 and 9/16, which could be bigger than 1/2. So that's kind of annoying. We're at least okay for some of the domain, but not the other bit. How else could we be okay? Maybe I should have tried this before. We could instead have that this solution, I guess the positive one is more convenient, is bigger than minus b. So let's try that instead. So that's slightly annoying. Instead, try the positive of case 2. So what was the positive of case 2? It was minus 1 plus square root (3 minus 4b) over 2. And I need this to be at least minus b. Well, minus 1 plus square root 3 minus 4b over 2, at least minus b, is equivalent to square root 3 minus 4b being at least 1 minus 2b. Did I remember my 2 before? Yes, I did. So b, is this always true, actually? Because it looks like it could be. I can say, if right-hand side is negative, we are done, right? Because square root is always positive. And if I now restrict myself to the right-hand side positive, because that's the only case when I'm not trivially done, this means that squaring is now reversible, because if I went the other way, any modulus can be neglected because its argument is positive. Then I can square to see that's equivalent to 3 minus 4b at least 4b squared minus 4b plus 1. They cancel. That's equivalent to 4b squared less than or equal to 2. So that's equivalent to b squared less than or equal to a half. That's the same as what we got before. So have I put my inequality the wrong way? I don't think we should have got the same. Let's take a moment to try to... We might come back to this. So x squared plus x plus b is 1/2. So x squared plus... If it's less than that, I get a minus x and a minus b. Yep. And if it's at least minus b, that's positive x squared plus x plus b minus 1/2. Right, I agree with my cases. Do I agree with my quadratic formula solutions? 1 plus or minus square root b squared, which is 1. Minus minus makes plus that. So I get 4b plus 2. So I agree with what I've written over 2. In the second case, I get minus 1 plus or minus square root b squared, which is 1, minus 4 lots of that. Minus minus makes plus. So I still get 3, but now I get minus 4b. I agree with my solutions. I agree that they're always real. For case 1, I want x to be less than something negative. So I said I wanted my negative solution to be less than or equal to minus b. So I've written that. I've doubled. I've made that the subject. 2b plus 1 on the left side. Yes. Both sides are clearly positive, so squaring is permitted. So I get 3 plus 4b, 4b squared plus 4b plus 1. They cancel. And I'm left with 4b squared less than or equal to 2. So I was happy if b squared was less than or equal to a half. But that's not true for the entirety of the domain, because if I was right at the door of 3/4, that would be 9/16, which is actually bigger. So there was no mistake there. Then I look at the positive scenario of case 2, which is minus 1 plus square root 3 minus 4b over 2. I want that to be at least minus b. I've multiplied through by 2, and I've brought the 1 over. So I get 1 minus 2b. If the right-hand side is negative, we're done. True, because a square root is defined to be positive. If I restrict to the case that the right-hand side is positive, that's the only time I am in any danger. Squaring is reversible, so I get 3 minus 4b, at least 4b squared minus 4b plus 1. And it looks like it's given me the same thing again. So we'll come back to that. That should only be a few marks anyway. And let's move on to part D. Sorry, that's what we were just looking at, part 2 rather. So part 2, I want to solve an equation. So, it looks very similar to what we had at the start, except I've now got z cubed. So why don't I play the same game to try to infer something like purely real or purely imaginary roots? Because that was what we were kind of dependent on in the last part. So I'll reverse engineer the same logic. Z cubed is 4 minus modulus z plus 2 squared. That means that z cubed is real. Okay, so if z is x plus iy, z cubed is x cubed plus 3 x squared yi minus 3 xy squared minus iy cubed. So that tells me that 3x squared y minus y cubed is 0. That tells me y 3x squared minus y squared is 0. So I don't get that the roots are real or imaginary, but I get that either y is 0, that would be pure real, or that y squared is 3x squared as my kind of other case. All right. So now I guess I can try to solve each case in turn. So if y is 0, then I can just sub in z is x, which is real. Having done that, I've got x cubed plus modulus x plus 2 squared is 4. But hang on a minute, a modulus is positive anyway, and something, if I square it, if it was negative, it would have just lost the sign. So that's just the same as this, right? The modulus at most is a sign variation, and the square would kill the sign anyway. So x cubed plus x squared plus 4x plus 4 equals 4. So x cubed plus x squared plus 4 is 0, I think, is what we get. Now, can we spot a factorization? I think -2 works, because I get -8 plus 4 plus 4. Yeah, so I can pull off an x plus 2. I need an x squared to give me my x cubed. I've got 2 x squares. I only want one of them, so I'll put that there. And then I better have a plus 2 to get the constant right. Quick sanity check. The x squared coefficient is -2. Sorry, I've got x cubed. And then I've got 2 x squareds. Sorry, that should be an x. There we go. Minus one of them makes x squared. The x's, I've got -2 plus 2. 0, good. And the constants are right. And then what's the discriminant of that guy? Well, it's b squared minus 4ac, which is -7, which is negative. So x equals -2 only. So that means that z equals -2 plus 0i is a solution. And now I can move to my other case. So my other case is that y squared is restricted by the fact that y squared is 3x squared. Now, I'm kind of pleased that the constraint is on y squared, because when I expand out the modulus, what's going to happen? I'm going to get a y squared in there because of the Pythagoras-y logic. So I think that's actually a good thing. So if I just write the thing out, yeah, because we said x squared, y squared was 3x squared. So I'm going to have to expand out the whole of z cubed. But in my expansion of z cubed, I know that I can kill the I bit because that's the whole point. So on that sort of locus, on that restriction, z cubed is just that, which is not so bad. So I get x cubed, and then I get -3 xy squared. And then I get my modulus. And my modulus is what? Well, let's write it explicitly. So at this point, I'm trying a general solution, which is x plus iy. So I've got x plus b plus plus 2 plus iy, because 2 is obviously real, squared equals 4. So that means x cubed minus 3xy squared. I don't get a square root because that thing's squared. So x plus 2 squared plus y squared equals 4. Now I'll replace all the y squared with 3x squared. X cubed minus 9. X cubed minus 9x cubed plus x squared plus 4x plus 4 plus 3x squared equals 4. Good, the 4's cancel. So if I collect everything on the right, I've got 8x cubed minus 4x squared minus 4x is 0. I think that's right. 8 minus 4 minus 4. Yeah, so I can pull off a 4x. 2x squared minus x minus 1 is 0. That factorizes to give me 2x minus 1 and x plus 1. So I get that x can be 0 minus a half or 1. So recalling that we've restricted here to y squared is 3x squared, which means that y is plus or minus root 3x. What are my new solutions? I get x equals 0, well, z rather, is 0 plus 0i. That's when x is 0. I get minus a half plus root 3 over 2i, and also the minus version. So these look like the third roots of unity, and if we really had our wits about us, we probably could have used that somehow. But equally, it's step 2, so they're not expecting us to know about that stuff. And then if x was 1, I get 1 plus root 3i and 1 minus root 3i, which is then going to join minus 2 plus 0i from earlier. And as a quick sanity check, z equals 0 clearly does work. Okay, we'll come back to that bit from D. Something funny happened there. Let's try to make some time savings. So looking at question 3, I think I know how to draw that graph. I think I can kind of see where the rest of it's going. Probably lots of taking logs to relate things to the graph. But inequalities can always be a bit fiddly, and I want to make up some lost time after what's gone wrong so far. So let's... question 5, integration. Right. Now we're talking. Let's try to get this one done quickly. And then that should make up. Hopefully we're about 5 minutes behind schedule. So let's see what we can achieve. So for part 1, we're told what substitution we want to make. So if x is 1 over u, well, the 0 limit goes to infinity. The infinity limit goes to 0. So if I call my integral I, which was 0 to infinity root x minus 1 over root x cubed plus 1, my limit, and I also better work out dx is minus 1 over u squared du. So I get minus infinity to 0, 1 over root u minus 1 over root 1 over u cubed plus 1 over u squared du. Okay, let's bring that u squared into the square root to clear nested fractions. I am thrilled beyond belief that the u squared becomes a u to the 4 when it goes in there. That will exactly kill the fractions we've got. So 1 over root u minus 1 over, so that 1 over u to the 4 becomes a 1, and the 1 over u becomes a u cubed. That's looking a bit similar to what we had earlier, actually, which is good. I'll swap the limits and use the minus to do that. So I get 0 to infinity, 1 over root u minus 1 over root 1 plus u cubed du. So I don't just want to solve this thing, I want to show it's 0. And I guess the most obvious way to show that something's 0 after a substitution is something like showing it's minus itself. This looks very, very similar to the original. I've just got slightly off powers. So let's multiply top and bottom by root u and see if that does us any good. So I get 1 minus root u over, yeah, we go, u cubed plus 1 du equals, because the integration variable is a dummy variable, the integral 0 to infinity, well, I'll put out a minus, root x minus 1 over that. I'll go back to writing x, which is minus I. Minus I is I, so I is 0. Okay, right, that was fine. Second part, I've got another substitution to make. So if x is 1 over u squared, dx is minus 2 over u cubed du. So if I call my integral, well, I'll just write it, 0 to infinity 1 over root x cubed plus 1 dx, Also note under this substitution, 0 goes to infinity. Infinity goes to 0. My limit swap, 0, infinity, 1 over u to the 6 plus 1. I get my minus 2, 1 over u cubed du. Okay, I'll play the same trick as before. I'll bring the u cubed in, and upon doing so, it's going to become a u to the 6 when it goes into the square root. That will give me a u to the, well, 1 plus u to the 6 if I preserve the order. And then I'll just swap the limits at the expense of a minus sign, and I get 2, 0 to infinity, 1 over root u to the 6 plus 1. And then I just want to go back to writing x. So I'll just say dummy. They know I mean dummy variable. I'm not calling the marker a dummy. Integral 0 to infinity, 1 over square root x squared plus 1 dx. As required. Okay, I think we're making up some lost time here. So now on to part 3. Maybe I've spoken too soon. So on part 3, I need to find values of p and s. Sorry, find in terms of p and s a value of r for which this vanishes. So I don't need to find all the values for which it vanishes. I just need to find something. So here's a crazy idea. What if I could play the same trick as in part 1? I mean, it's a very similar thing to part 1. We wanted to show that this integral is 0. If I were to substitute 1 over x, or x equals 1 over u again, maybe I can then fine-tune r so that I get the same integral as what I had in part 1, or something else good might happen to give me 0. Or maybe just minus itself. That would probably do the job as well. So let's try and play that trick. If that fails, we can try something else. But, I mean, substituting that thing from part 1, I can't really think of anything else they would possibly expect me to do here, other than maybe to repeat the substitution from part 2. But in part 2, I wasn't showing that something was 0. So this feels a bit more natural to me. So if I set x to be equal to 1 over u, again, I get dx is minus 1 over u squared du. 0 maps to infinity. Infinity maps to 0. So what do I get? Okay, well, I get infinity to 0. I get my minus. I get 1 over u to the r minus 1 over square root 1 over u to the s, 1 over u to the p plus 1 all over u squared du. So I'll swap the limits around at the expense of the minus. And I will bring the 2 in. So if I bring the 2 in, I've now got u to the, well, when it goes in, it becomes a 4. 4 minus s minus p plus u to the 4 minus s. And I don't like these nested fractions, and I'm starting to think maybe I'm going to try to make this minus itself rather than literally what we had in part 1. So I'm going to multiply through by u to the r, top and bottom. So I get 1 minus u to the r. Now, when the r goes into the denominator, it becomes a 2r. So u to the 2r plus 4 minus s minus p plus u to the 4 plus 2r minus s du. Now, if I have that these powers are the same as in the original, then because my numerator is the same as what I started with, just out by a minus sign, doesn't matter that it's a u, dummy variable, right? If that's the case, then I would be able to declare that it's minus itself. So I need one of the powers to be 0 because I wanted... Oh no, I'm sorry, that's not quite true. I want one of them to be s and one of them to be p minus s. So I could have either that this one is s plus p, and this one is s, or I could have the following pair. So that's an R, to be clear, not an S. 2R plus 4 minus S minus P equal to S, and 4 plus 2R minus S equal to S plus P. Then I is minus I, so I is 0. So each of these is a system of simultaneous equations in really only one variable. R's the only variable. So I'm counting on a miracle here. I need both of the things to happen to be 0. Or both of the equations rather to happen to be simultaneously solved. But this is a step question. Miracles might well happen. Let's start with case A. So for case A, remember I'm solving for R. So what would I get? Equation 1 would tell me that R is 2S plus 2P minus 4 over 2, which is S plus P minus 2. And then if I plug that in equation 2, the LHS is 4 plus 2S plus P minus 4. Oh, minus S, right? So that's my 2R, which is S, which works. So that means that if I choose R to be S plus P minus 2, case A is met. So my integral is minus my integral, so my integral is 0. So if I wasn't trying to make up lost time, I would now do case B as well and just see what happens there, just in case I've made a mistake or something. I'm assuming if I did that case, I would find that the value of R that works for one equation would actually not work in the other one. I assume something like that would happen. Again, you know, if time permits, I might come back and check this, but I think that's fine. And then part 4, well, if part 3 was generalizing part 1, part 4 is clearly generalizing part 2. Therefore, I want to make a substitution more like the one of part 2. And given that the fact I got a 2 on the right-hand side in part 2 was from the u to the minus 2, from differentiating that, I bet I want to substitute x equals u to the minus k, right? It has to be, because then dx involves a minus k, and it looks nice and plausible. So dx is minus k u to the minus k minus 1 du. Because k is positive, I know that infinity maps to 0, 0 maps to infinity. If k were negative, that would not be true, so that's important. And then what happens to my integral? 0 to infinity, 1 over square root x to the p plus 1 dx. My limit switch over, infinity, 0. Minus k, I'm very happy about that k. 1 over square root x to the, 1 over u to the pk plus 1. 1 over u to the k plus 1 du. I'll use the minus to switch the limits around. So I've got 1 over u to the pk plus 1 times that. Now, when I bring that in the square root, it becomes a 2k plus 2. So I've got u to the 2k plus 2 minus pk plus u to the 2k plus 2. Now, what do I want to achieve? I want to achieve the fact that one of these powers is 0 so that I get my plus 1. That is not going to be 0 without k being negative, which is no good. So I want, therefore, that 2k plus 2 minus pk is 0. And that means that I want that k is 1 over p, well, 2 over p, k, sorry, I'm trying to solve for k. What am I doing? So if I solve for k, sorry, I've got p minus 2 lots of k is 2. So as long as I choose this, and yeah, so that's fine. So I choose k equals 2 over p minus 2, because then that becomes u to the 0 and I get something good. Now, that's only any good if p is at least 2. But what happens if I invert that? What if I make p the subject instead? Well, that means that p minus 2 is 2k, so p is 2 plus 2k, which is bigger than 2 as k is positive, so that's good. My k choice really is positive. So I've said what p is in terms of k. I wanted to give p and q in terms of k. And then what is q? Well, q is what the surviving power becomes, which is 2k plus 2. So that's it. So I then get k integral 0 to infinity, 1 over square root u to the q plus 1 du as defined, which is k integral 0 to infinity, 1 over square root x to the q plus 1 dx, dummy variable. Okay, so integration has come to the rescue. That's the end of that problem. We're now 12 minutes ahead, which is better than being behind. Question 6 looks a bit like question 1 in that I don't say anything conceptually bad, but it looks pretty heavy. And I want to get more ahead on time. I'm worried about my timing. So I'm going to do, question 7, differential equations. This doesn't look too bad. I may come to regret that, but let's have a stab at question 7. So first of all, this is a second order differential equation. However, this is step 2. They're not expecting me to know about auxiliary equations, not that that would even apply here. So there must be some trick. But would you look at that? The right-hand side is clearly a pure derivative, right? It is clearly, by the chain rule, the derivative of x squared, because I would get my 2x and then a dx by dt by the chain rule. Now I can integrate both sides with respect to t. dx by dt is x squared plus c. Now, I'm looking at the case where dx by dt is a squared when t is 0. So at t equals 0, I know that x is a, and dx by dt is a squared. So I get a squared equals a squared plus c. That means that c is 0. So I found that dx by dt is just x squared. And now that's obviously variable separable. So 1 over x squared dx is 1 dt. So minus 1 over x plus d is t. So that means that 1 over x is d minus t. So x is 1 over d minus t. And now I just want to test for the value of my constant. So I know that when when t is 0, x is a. So a is 1 over d minus t. So d minus t is 1 over a. So d, what's that t doing there? Sorry, there is no t. We've subbed in t is 0. So d is 1 over a. There we are. So that means that x of t is 1 over a minus t, which is a over a minus t. Okay, we've solved. What happens as t increases from 0? Okay, well, t increases from 0 means that the denominator shrinks, so x grows. So that means I move in the positive x direction away from my starting point, which was x equals a. So I'm moving in the positive direction. Okay, that wasn't so bad. What about part 2? So in part 2, well, it's the same differential equation, but just different boundary conditions. So I can say same as part 1 up to where I started plugging things in. So that was when I said dx by dt was x squared plus c. Okay. So I plug in at t equals 0. At t equals 0, x is equal to a, and dx by dt is equal to a squared plus p squared. So that means a squared plus p squared is a squared plus c, so c is p squared. So I've now got dx by dt is x squared plus p squared. I'm feeling much happier now we're doing calculus. So 1 over x squared plus p squared is dt, dx, integral. P is positive, so I don't get a modulus when I use the formula book result to integrate that. We could do it from scratch, but it's a quotable result, so I will do so. Okay. Let's find... Oh, I should use a d now, because it's a different constant. So at t equals 0, x equals a, and dx... Oh, and I don't need dx by dt anymore, sorry. So I get 1 over p arctan x over... No, a over p is equal to d. So that means that 1 over p arctan x over p is this. So I get my 1 over p there. Now I multiply through by p. And then I guess I'll just take tans. So tan of arctan, I can cancel. It's only when you do arctan of tan, you're going to get a potential plus n pi. So now I get x over p is tan of pt plus arctan q over p. I mean, I could use compound angle to expand this out, but it's not really clear to me what it would achieve as such. So I think I'll probably leave that as it is. So I get that x of t is p tan pt plus arctan. Okay, now what happens... Have I made an algebra mistake? I just want to... quit. This felt too easy, so I want to just very quickly check that I've plugged things in correctly. 1 over p arctan a over p is d. 1 over p arctan x over p is t plus that, multiplied by p. Yeah, okay. So when I increase t now from 0, I mean, tan is sometimes increasing, and, well, no, tan is always increasing as long as you don't cross an asymptote. But I guess I can say this. As arctan q over p is by definition acute, as t increases from 0, the tan's argument becomes a bigger positive acute angle. So that means that x increases. So that means that I move in the positive direction away from my starting point, which was, again, x equals a. Okay. If we can do this next bit in 3 minutes, we're now 30 minutes ahead. So that's a bit of an improvement on where we were earlier. But again, doing the last part in 3 minutes might not happen. So it's the same differential equation again, just different boundary conditions. So again, it is the same as part 1 up to the point where we had dx by dt equal to x squared plus c. But now I know that at t is 0, I have that x is a and dx by dt is a squared minus q squared. So that means that a squared minus q... Oh, I see where this is going. We're going to get the same thing, but a minus on the denominator. Okay, c is minus q squared. So that means that dx by dt is x squared minus q squared. So 1 over x squared minus q squared integral dx is integral 1 dt. Now I could use hyperbolics, but this is step 2, so I'm not going to. Instead, I can use partial fractions. So I am going to be really naughty and try and do it just by looking at it. So if I do 1 over x minus q plus 1 over x plus q, no, with a minus, that gives me 2q over that denominator. So I just need to divide by 2q. There we go. That's bought me a bit of time. So I get 1 over 2q integral 1 over x minus q minus 1 over x plus q dx is integral 1 dt. So those are both going to be log integrals that I can then combine. Yeah, they're always very sloppy with their moduluses in the mark schemes, but I'm going to be at least initially careful, and then I might decide not to bother. So x minus q over x plus q equals t plus d. Okay. Do I know whether the argument of that modulus is positive or negative? Not really. I guess I can kind of see that if it starts positive, it's always positive, and if it starts negative, it's always negative, perhaps, from the differential equation. Well, I'll tell you what, we'll worry about that. That could be kind of subsumed into the arbitrary constant. So let's just for now ignore it. I bet the mark scheme will do the same. So we get that equals 2qt plus 2qd. So that means that x minus q, yeah, because it would just be a minus that I'll be able to subsume into other stuff. I think it's fine. Have to admit, my stamina is taxing, which is why when you're doing step for real, you do need to do regular time mocks, or like me, you'll start to get too tired. So e to the 2qt, e to the 2qd, I will define this as a. So I get x minus q over x plus q equals a e to the 2qt. Okay, so I can make x the subject quite easily. I haven't figured out what the constant is, but I'll probably do that once I've made x the subject. So what have I got then? I've got x minus q equals aeq to the tx plus aq e to qt, and I've dropped a 2. I've dropped an x. Goodness me, we've got to be careful. Ax e to 2q2 plus x And the same thing with a q instead. Good. So x, therefore, is q 1 plus a e to qt over 1 minus a e to qt. Now I'll try and find my constant. So x is a at t is 0. So that tells me that a is q 1 plus a over 1 minus a. So a minus aa is q plus qa. So a is a minus q over a plus q. So that means then x of t is q over, well, let's just factor off the q. It's a bit horrible, but so be it. A minus q over a plus q over 1 a minus q over a plus q. I think that was a minus a and a plus a. E to the 2qt, e to the q2qt. Okay, we've solved for it. Now I need to talk about what happens again when t increases, splitting into cases according to t, whether I move away or towards the origin, the cases that arise. Clearly what matters is whether a is bigger than q, equal to q, or negative, or less than q rather, because that will tell me whether these coefficients are positive or negative. So first of all, if a is less than q, a minus q over a plus q is negative. So as t increases, the numerator, I mean, that gets bigger, but because that's a negative coefficient, the numerator shrinks. The denominator, that gets bigger, but minus minus is a positive, so the denominator grows. So that means that x decreases, and I move in the leftwards direction. So I guess towards the origin. From x equals a, I'm going to go towards the origin. If a is equal to q, then actually those coefficients are just nothing, and I actually just get that xt is just q constant. And in that case, the particle doesn't move. And finally, if a is bigger than q, well, a minus q over a plus q is positive. So that means that as t increases, now the numerator grows and the denominator shrinks. So that means that x grows, so x moves in the positive direction away from x equals a. Okay, that's another question done. So that's in theory 4 done, although if I have the stamina at the end, I want to return to that funny business in question 2. What should I do next? So I don't like the look of question 8. Those sums look painful. In principle, I should do some mechanics. I mean, really, technically these days, I'm as much a physicist as a mathematician, but something about the mechanics questions is scary. I think I did choose some when I took STEP for real, but that was when I was young and bold. I don't have the guts now, so I'm going to go past that. Oh, I like the look of question 11. So we've got some pretty easy summations by the looks of things. I can kind of envision the sorts of games that I'm going to play for parts 1 and 3. Yeah, let's do it. Let's go for 11. And if we can blitz 11 pretty fast, 23 minutes, we'll have an hour to do one more question and hopefully complete question 2. That is if I don't collapse of exhaustion first. So, okay, 11. By considering a geometric series or otherwise, show this thing. Well, okay, what's a geometric series? It would be r equals 1 to infinity x to the r. I could have done x to the r minus 1. Doesn't matter. It's just off by a power of x. That would be first term over 1 minus common ratio for this. Now, I know this trick. If I take an x derivative across both sides, I can bring the derivative through and I can drop the power. So I get sigma r equals 1 to infinity, rx to the r minus 1. And then, well, that's the same as 1 minus 1 over 1 minus x. And it's a show that, so I better be thorough. I was going to do the differentiation in my head, but it's a show that. Let's show all the steps. Low d high minus high d low over the square of what's below, which is 1 minus x plus x over 1 minus x squared, which is 1 over 1 minus x squared as required. Okay, that's part 1 sorted. Ali plays a game with a fair 2k-sided die. He rolls until he gets a 2k. He wins if all the numbers he rolls are even. Find the probability that Ali wins the game. Well, the problem is there are lots of winning sequences he could have. So why don't I split into cases according to how long his run is before he wins? So the probability that Ali wins after R throws because he has to get a string of even numbers ending with a string of even numbers that are not 2k. So that means there are 2k numbers and k minus 1 of them are good because k of them are even, but we don't want to be getting 2k because we don't want to win too soon. I have to do that r minus 1 times, and then I have to get a winning throw of a k. So that is r minus 1 non-2k evens followed by rolling 2k. So if I think about like a probability tree, these are all my good ends of branches, so I just need to add them up. So that means that the probability that Ali wins, well, R can be anything, I guess from 1 to infinity, right? There's no upper limit to how long the game can go on for. I can pull the 1 over 2k out, and I get k minus 1 over 2k to the r minus 1. That's an infinite geometric series. I know that the magnitude of k minus 1 less than 2k less than 1 is equivalent to the magnitude of k minus 1 less than the magnitude of 2k. K is positive, so that's equivalent to k minus 1 less than 2k. That's equivalent to k greater than minus 1, which is true, so it applies. So then that's equal to, first term, well, to the power of 0 is 1 over 1 minus the common ratio. Okay, so 1 over k plus 1. Does that make sense? So, quick experiment. What if k is enormous? If k is enormous, Ali is very likely to lose because his odds of the winning throw is extremely low. He's expecting to have a really, really long string of throws, and it's very likely in a long string he gets an odd somewhere. So the answer should tend to 0 when k tends to infinity. Indeed, it does here. Likewise, if k is 1, then he either wins... if k is 1, he's got 2 sides. He either wins immediately or loses immediately, so the answer should be a half, and it is. So this all looks reasonable to me. Now, it's pretty obvious that in part 2, we're going to need to use the result from the last part. So the expected winnings, well, how does he win R pounds? He wins R pounds precisely by winning after R throws. So actually, this thing from earlier is now going to be useful in its own right. So let's write that more efficiently. So the expected winnings is going to be sigma R equals, he could win £1 if he wins straight away, or he could win any number of pounds if he keeps going. R, probability A wins with R throws, and happily, we worked that out earlier. So that is going to be, well, what was it? It was, I've got my 1/2k that I'll pull out. Sigma. R equals 1 to infinity. I'm exhausted. This is more tiring than I thought. If you're doing step this year, please do lots of time marks. You don't want to be flagging like I am. So wins after R throws, k minus 1 over 2k to the R minus 1 times R. Okay. This is clearly part 1 with X identified with that, which we already verified in the last part, obeys magnitude of X is less than 1. So, so that's fine. I can just use the result, right? So 1 over 1 minus that thing all squared, which is 1 over 2k, 1 over k plus 1 over 2k squared, which is 2k over k plus 1. Cool. Okay. Part 3. That's got to come from differentiating a binomial expansion or something. Or even just, yeah, because if I took a binomial expansion, I would get things like n choose 1 and n choose 2, but I wouldn't get the coefficients of 2 and 3. But playing the same trick as part 1, if I differentiate it, I should get somewhere. So let's start with this. This might be the wrong thing to consider, but let's start with this. Now, if I differentiate that, I'm not quite going to get the right stuff. Because I'm going to get, for example, on my n choose, or well, actually, yeah, because I won't get any x's at all on my n choose 1s, and I'll get x rather than x squared on my n choose 2, and my coefficients will be slightly wrong. I don't want to use to a power of n plus 1, because then my chooses will be off. I'll just multiply it through by x to bump all the powers up by 1, I think, is what I need to do. N choose 1, x squared, n choose 2. I should really do this all in sigma notation, but I've started now. So if I take an x derivative, the right-hand side becomes exactly what I wanted, I think. 2 n choose 1 x plus 3 n choose 2 x squared, and so on through to n plus 1. N choose n is just 1, x to the n. And the left-hand side becomes, by the product rule, x, n, 1 plus x to the n minus 1, plus 1 plus x to the n, which is 1 plus x to the n minus 1, nx plus 1 plus x, which is 1 plus x to the n minus 1, 1 plus n plus 1, x. So that is my answer. Okay, we're getting somewhere. Part 4. Zen plays a different game with a fair 2k-sided die. She rolls the die until the first 2k appears and wins if the numbers rolled are strictly increasing. If she wins, she earns £1 for each roll. If she loses, she earns nothing. Okay. So I clearly want to work out the probability that Z wins in R throws, because that's what I want to multiply by R and then take an appropriate sum over. Now, what does that mean? That means we get an increasing sequence of length R minus 1, and then we get 2k. All right. How many increasing sequences are there of length R minus 1? Well, all I have to do is, I can't use up 2k because then the game's ended. So from 1 to k minus 1. Sorry, 2k minus 1. So from my 2k minus 1 things, I just need to choose R minus 1 of them. They're the ones that are going to be my increasing sequence. And once I choose which numbers to use, the order is fixed by the requirement that it's increasing. So that is how many increasing sequences there are. And the probability, so this is the number of increasing sequences. The probability of a given increasing sequence of that length is obviously this, because I've got a prescribed outcome for every throw, and each score happens with probability 1 over 2k. So this is the probability of a given increasing sequence. And then I've also, at the end, got to get the 2k. So that's the probability that I get my increasing sequence of length R minus 1 from 1 to 2k minus 1. And then I have a further 1 over 2k from the end. So this is looking a little bit like the sum we just studied. So that means that the expected value of Z's winnings is sigma. Now, this is only finite, right? Because she can't... The most throws she could possibly have is 2k. She could go 1, 2, 3, 4, blah, 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 up to 2k. But strictly increasing means we can't use repeats. So the most you could win is 2k. And then I do R times this thing. Now, this looks a bit like the result from part 3, except there... Clearly, the power started from 0 and not 1. Because we started with x to the 0, not x to the 1. So I'll make a change of counter variable. I'll introduce a t, which is r minus 1. So t runs from 0 up to 2k minus 1. R is t plus 1. 2k minus 1 choose t. 1 over 2k to the t plus 1. And I'll go back to writing it in R language because I prefer that. How does this compare to what we had in the last part? That's what I want to know. So on the other hand, 1 plus 2n choose 1x plus up to m plus 1 x to the n. So I'll let my sum run over the powers. The coefficient is always 1 more. And then I've got n choose my power. And then I've got x to... Well, to the r, right? Not to the r plus 1. But that's fine. I'll turn that to an r, and I'll pull a 1 over 2k out. So that means if I call this thing star, so star is part 3 with n identified with 2k minus 1, and x identified with 1 over 2k. So what does that equal? Hope this comes out as something reasonably pleasant. 1 plus x to the n minus 1. 1 plus x to the n minus 1. And then I think in the other bracket, we had 1 plus m plus 1x. So m plus 1 is 2k x. Oh, well, that's kind of nice, right? That's just a 2. Really? That seems too good to be true. N plus 1 is 2k x. Yeah, okay, awesome. So that's just 2 lots of... got to be a bit careful. Remember, there was that 1 over... So E winnings, we did pull out a 1 over 2k. I've got to remember that. So I've got 1 over 2k, 1 plus 1 over 2k to the 2k minus 2 times 2, which is 1 over k, 1 plus 1 over 2k to the 2k minus 2. Which I guess is fine. Yeah, I don't see a problem with that formula. Frankly, I'm too exhausted to think of a sanity check, but the answer seems reasonable. And we're also going to get a nice cross-check, actually, on part 5, because we're meant to do some approximation, and I'm assuming that if we don't get 35%, then we'll know something's gone wrong. Okay, on to part 5. If we could do this in less than 7 minutes, we have a whole hour to do one more question. So we're hopefully going to survive this. Right. I want to know how much Zens are more than Allies, so I will just do a ratio, right? So E Ally over E Zen. Now, what was E Ally? That's the problem. 2k over k plus 1. And then that's all over 1 over k. 1 plus 2k to the 2k minus 2. 1 over 2k. And the 2k minus 2. I like that, because that looks a little bit like this E thing we were thinking about. Oh, but let's do Zen over Ally, sorry, because Zen is meant to be bigger. So let me just swap that around a minute. So I get 1 over k, 1 plus 1 over 2k to the 2k minus 2 over, what did Ally get? 2k over k plus 1. A bit distressed about... Let's see. I'm a bit worried about the powers, to be perfectly honest. Because... Have I got Allies wrong? Have I done something silly with Allies? Did I forget a square or something? Oh, I did! Right. That has a square from there. Because I was thinking it looked like I was going to get something that clearly tended to 0, not a finite quantity. Okay, thank goodness we spotted that, because now that has a square on it. Now, okay, this looks much better. And was that even a 2k? Now I'm questioning everything I did with Ally. I think it was 2k. Okay. So k plus 1 squared over 2k squared times this thing. Now, if that were the same as that, then I could use my result with n being 2k. So I'm going to pull 2 of them off. So I'm going to say that I've got 1 over 1 plus 1 over 2k squared. And then I've got it to the k, to the k, 2k rather, up there. So now bit by bit, this tends to 1. This is a k squared over a 2k squared, so it tends to a half. And this, by the result, tends to e by given with n being 2k. So this thing, as k tends to infinity, I've got 1/2 e. Well, e is approximately 2.7. So 1/2 e is approximately 1.35. So Zen wins 35% more. Okay, lovely. And that's a really good sanity check on both parts 2 and 4, because if, as actually happened, there was a mistake in either of them, that wouldn't have come out correctly on the nose. So I'm confident in that answer. We have an hour and 2 minutes to do one more question. And then if I have the energy, I'll try and find what went wrong with part 2. Now, I could do this stats question, question 12. But you know what? I'm going to go back to question 3 because I kind of know where question 3 is going, right? I mean, it's a really classic interview question. Is e to the pi or pi to the e bigger? And you deduce it using these sorts of methods. So I kind of have a feeling, at least at the start for where this is going. I'm guessing optimistically my marks must be in the 90s by now, hopefully. So if I can just get a solid partial here, I should be set for an S. And if I can get an S when I'm this out of practice, I'll be happy. So let's go for 3. I may regret it. If it goes really wrong, who knows? Maybe I can try a 7th question, but I think I might drop dead before I finish. So first of all, I have to sketch the graph. Right, y equals ln x over x. So as x tends to 0 from below, ln x tends to minus infinity, x tends to tiny positive, so y tends to minus infinity. So it's undefined there, but I'm thinking about what it does. And sorry, it tends to x from above, because negatives are illegal. As x tends to infinity, y tends to 0, and that's because polys beat logs. So obviously the numerator and the denominator are both getting big, but the numerator gets big more slowly. And then I guess I can check turning points. dy by dx is low d high minus high d low over the square of what's below, which is 1 minus ln x over x squared. So TP at x equals e, for which y is 1 over e. And I guess we can see from the shape, because I've said what it does there and there, it must be a local max. So there's no need to look at second derivatives. Okay, let's sketch the thing. So I've got an asymptote. I obviously cut at 1 because ln of 1 is 0. I go up. I turn around at e 1 over e. And then I asymptote to 0. And let me make it a bit clearer that I do. So distort the graph a bit. I think that's acceptable. That looks a bit like an inflection point. Shouldn't do that. Let me do it a bit more organically. So it's harder to draw with a slippery iPad screen than paper, I'll say that much. So something like that. That'll better do. I think that'll be fine. Okay, so part 2, I need to show some things. So I'm going to, first of all, I'm going to take logs across the inequality because I want to manipulate it into something that looks like ln x over x. So I'm going to note the following. So I'm going to make it clear to the reader. I'm telling them something I'm going to repeatedly use. Taking ln across inequality is fine as ln x is an increasing function. And it is also reversible as can take e to the x across, which is also increasing. So I'm going to repeatedly do reversible manipulations on the inequalities, and I've just cleared the air straight away with why this is legitimate. So now in part A, 3 to the pi bigger than pi to the 3 would be equivalent to pi ln 3 bigger than 3 ln pi, which would be equivalent to ln 3 over 3 bigger than ln pi over pi, both divisors positive. And then I can say, well, look, 3 and pi are both bigger than e, so they're past my max at x equals e, but pi is bigger than 3, so further away. So that means that from my graph, I know that ln pi over pi is smaller than ln 3 over 3, so true. So now can start from ln pi over pi less than ln 3 over 3 known, and read backwards. And I'll just say will use throughout, because I know that sixth formers are very bad at understanding and communicating the directionality of logic. So I know the marker is going to be strictly trying to see if I'm spuriously reasoning backwards. I've explained it very clearly here, and then I'm not going to write this every time because I've explained why these manipulations are legitimate. Okay, what about part B? So 9/4 to the root 5, bigger than root 5 to the 9/4, is equivalent to root 5 to the ln 9/4, bigger than 9/4 to the ln root 5. Put it into log x over x form. That's equivalent to ln of 9/4 over 9/4, bigger than ln of root 5 over root 5. Now, who is bigger? So let's tell the reader that I'm now going to consider that question. Well, I can compare them by squaring. So 9 over 4 bigger than root 5 would be equivalent to, squaring both, 81 over 16 bigger than 5, but that's the same as 5 and a 16th bigger than 5, which is true. So that means that 9/4 is bigger than root 5, and clearly 9/4, which is 2.25, is smaller than e, which is about 2.7. So both x equals 9/4 and x equals root 5 are to the left of the max at x equals e, but the bigger number, 9/4, is closer. So that means that ln of 9/4 is actually bigger than, over 9/4 is bigger than ln of root 5 over root 5 from the graph. So star, true, and then again, read backwards, and this implies as required. Okay, that's got to be 6 marks on the question so far. I'm feeling pretty confident that I might have nabbed an S, but who knows? I might have done something really stupid that I haven't realized. So I'm going to try and push a bit more. I need to decide which of these guys is bigger. Ooh, okay. Well, let's play the same game. X to the x plus 2 bigger than x plus 2 to the x would be equivalent to x plus 2 to the ln x bigger than x ln x plus 2. That would be equivalent to, so x is bigger than 1, so my divisors are positive. that would be equivalent to ln x over x bigger than ln of x plus 2 over x plus 2. But they both depend on x. It's not like I can compare where they are to the turning point. Okay, that being said, the right-hand side is the left-hand side translated by minus 2, 0. So maybe I can reason graphically here. Feel like I'm not doing what they're intending me to do, but that's okay. They haven't said I have to use anything. So the original graph was like that. And now I'm going to have another version. So my asymptote is going to be at minus 2 rather than at 0. So it's going to be like this. So its turning point is going to be, well, at e minus 2, which is a tiny positive. Well, not that tiny, but a bit tiny. So then it's got to decrease after that point. So there can only be one intersection. So this is y equals ln of x plus 2 over x plus 2. This is y equals ln x over x. Clearly, one intersection from graph. And I'll say it's at, I don't know, x star. Now, I can't solve this equation. I mean, how would I even begin? Right? By algebra, because there's two different logs. Maybe it could be done, but I don't fancy doing it, I'll say that much. Can I just spot a solution? If I could just spot a solution, then because I've said it's unique, it would be the only solution. Oh, well, x equals 2. Can it be? Because ln of 4 over 4 is ln of 2 squared over 4, which is 2 ln 2 over 4, which is ln 2 over 2. So that means that x star is 2. Marvellous. So below, now we're on a roll. This is deduced to be 2. This is exactly what I feared, though, with these inequality questions. That there'd be something weird that you just have to spot. And if you don't spot it, you're toast. So from my graph, there is 1, there is 2. I can see that the x plus 2 graph is higher. So from my graph, ln of x plus 2 over x plus 2 is actually the higher of the two on 1 to 2. And I'm so worried I'm going to mess up my reversible logic that I'm just going to do it backwards. So that implies that. That implies that. And that implies x plus 2 to the x is bigger than x to the x plus 2 on this domain. Okay. That was a bit weird. I'm sure I'll kick myself when I look at the mark scheme and see that there's something much more obvious we could have done. But I think that argument is completely fine and works. Right, let's see if we can finish this one. I think if we can get to the end of this, I'll be satisfied. Not sure I'm going to have the energy to go back to question 2. I need to show that some inequalities are equivalent in part 4. Oh, well, that's just going to be laws of exponents, right? So 9 to the root 2 is 3 squared to the root 2, which is 3 to the 2 root 2. Bingo. And root 2 to the 9 is 2 to the 9 over 2. And I want a 2 root 2, which is 2 to the 3 over 2, which is the case by my laws of exponents, which is 2 to the, which is 2 root 2 cubed. So that tells me that 9 to the root 2 is bigger than root 2 to the 9. That's equivalent. That is what I started with. That's equivalent to this thing. And this is obviously of the form that we're now experts at dealing with. Okay, so we're now going to play the same game. So that would be equivalent to 2 root 2 ln 3 bigger than 3 ln 2 root 2. My hand's hurting. Dividing, that is equivalent to ln 3 over 3 is this. Yeah, I have to admit, I'm finding this a lot more exhausting than I thought. Ln 3 over 3. Oops, I flipped my signs over. No, I haven't. It's pointing the right way. Okay. Now, the problem is 3 is to the right of the maximum at x equals e. Oh, no, 2 root 2 is to the right as well. And 2 root 2 is bigger than 2 times 1.4, which is 2.8, is bigger than e. So I have got e, then 2 root 2, then 3. So both are to the right of the maximum at x equals e, but 2 root 2 is closer. And just to justify that, I mean, 2 root 2 squared is 8, which is less than 3 squared, which is 9. So if 2 root 2 is closer to the maximum, that means ln of 2 root 2 over 2 root 2 is actually bigger than ln 3 over 3. Again, I'm now worrying that they're going to be really annoying about my reversibility, or that I'm just going to mess it up. So let me just actually do the working backwards. Ln 2 root 2 cubed is bigger than ln 3 to the 2 root 2, which implies 2 root 2 cubed is bigger than 3 to the 2 root 2, which by earlier is the same as saying root 2 to the 9 is bigger than 9 to the root 2. Okay, one part to go, 45 minutes on the clock. Part 5, decide with justification which of these is bigger. Well, I'm going to have to play the same sort of game, right, as in the last part to get these into a form where you've got the same base and argument just switched over. So 8 is a power of 2. So I'm going to say 8 to the cube root of 3 is 2 cubed to the cube root of 3, which is 2 to the 3 cube root of 3. Okay, and to see what I want to do, let's massage both at once. I mean, in part 4, I knew what my target was for both of these guys. Whereas here, that's not the case. So cube root 3 to the 8 is 3 to the 8 thirds. So I want it to the power of one of my bases. Sorry, I want it to the power of the base of the other one, is what I meant to say. So this should be really simple. I'm drawing a blank. What am I trying to do? Let's write everything in terms of just powers. So that is 2 to the 10 thirds. So could I do like that is I don't know, 2 to the 2/3 to the 5, but I'm not going to get anything like that. Yeah, if I wasn't exhausted, this would probably be obvious to me straight away. Well, I have an 8, which is a 2 cubed. That's kind of got to be the root in. So what if I write that as 2 cubed to the... But it would have to be to the 10/9, which I really don't like. Have I just messed up my exponent rules? 8 is 2 cubed. That's being multiplied by a cube root of 3. That's 9 plus so 3 plus a third, which is 10 thirds. So I definitely don't want a 10/9 as my power. That's just completely unhelpful. What if I try to make it a 2 squared instead? Because if I do that, that becomes... And I also kind of like 2 squared because I'm thinking back to part 3 where we saw there was something significant about the numbers 2 and 4. Can I achieve anything with that? Sorry, is that even right? I'm writing complete nonsense, aren't I? That's what's gone wrong. That and that are completely different things. Right, now we're talking. So I've actually got, 2 to the 3 to the 4 thirds. Okay, that is a bit better. So 2 to the 3 to the 4 thirds, which is the same thing as 2 to the 3 to the power of a third. Because 2 to the 3 to the power of a third would be 2 to the 3 times a third. No, what am I saying? Oh my goodness me. I think that's right. Because 2 to the 3 times... No. To the power of 3 to the third. There we go. Because then I get 2. This is extremely elementary stuff. I've never lived the experience more of when I tell students to do regular mocks because of stamina, because this is ridiculous that I'm even struggling with this. But when you're going for 2 hours, 2 hours 20, it does start to wear you down. Right, this is correct, because 2 to the 3 to the 3 thirds is 2 to the 3 times 3 to the third. That is 3 to the third, which is 2 to the 3 to the 4 third. Right. I bet I can write this as the converse, because that would be 3 to the thirds to the 8. There we go. Okay. Thank goodness for that. We've managed, I think, to write this in a sensible form. So I can say, therefore, that 8 to the cube root of 3 being bigger than cube root of 3 to the 8 is equivalent to 2 cubed to the 3 to the third bigger than 3 to the third to the 2 cubed. That is equivalent to 3 to the third ln, and I'm not going to use log rules because I want my ln x over x structure. That is equivalent to this. Two to the 2 cubed is obviously way bigger than 3 to a third. This is too simple. Something funny's happened. Probably with my laws of exponents again. Let's just double check this. Stay calm. We've got, in principle, nearly 40 minutes. 8 to the power of the cube root of 3 is 2 cubed to the cube root of 3, which is 2 to the 3 times cube root of 3, which is 2 to the... Yeah, so 3, I've got one of them and the third of them. So 4/3 of them, which is 2 cubed to the power of 3 to the third, because that's 2 to the 3 times 3 to the third. Okay. Now, at this point, so I think that's fine. 2 cubed to the 3 to the third. The other one is cube root of 3 to the 8th, which is 3 to the 8/3. I think I agree with that. Which is 3 to the third to the 2 cubed. So I don't see an issue with what we've done here. That seems fine. So 8 to the cube root 3, bigger than cube root 3 to the 8, is equivalent to 2 cubed to the 3 to the third, bigger than 3 to the third to the 2 cubed. The size of those bases is really bothering me a lot, because it's just obvious, right? That 2 cubed is way bigger than 3 to the third and way bigger than e. Well, perhaps that's the point. One of them is to the left of e, one of them is to the right of e, and it's not obvious who's further or who's dropped down more. Okay, maybe we're good. So 2 cubed is 8. So this is way to the right of x equals e, which is the max. 3 to the third is, definitely smaller than e. So it's to the left of x equals e, which is the max. So I can no longer say, oh, well, they're both to the right, but you're more to the right or something, because it's not obvious that being a fixed amount to the left is equivalent to being a fixed amount to the right. This is a little bit difficult now to compare. Intuitively, you would think that this is way smaller because it's way further, but how can we prove it? Can I link back to my knowledge? I'm finding myself coming back to this funny fact we had earlier, that ln 4/4 is ln 2/2. Because that's a point on the right, that's a point on the left. So it gives me a kind of ground for comparison. How about this? If this works, I'll be very happy. I know that 2 cubed is bigger than 4, which is to the right of the max. So that means that ln of 2 cubed over 2 cubed is smaller than ln 4 over 4. Now, I'm going to try and compare the other guy to ln 2 over 2 because I know from earlier it's secretly the same thing. So 3 cubed being bigger than 2, that would be equivalent to 3 being bigger than 8, which is false. So that means that 3 cubed is smaller than 2. I've cubed both sides. I'm comparing it to 2, which is the other value. So that's equivalent to that. So that means that 3 cubed is actually smaller than 2, which is itself smaller than e. So again, I'm further from the max. So I know that ln of 3 to the third over 3 to the third is smaller than ln 2 over 2. That's a real shame, because I thought we might be able to compare each of them to ln 4 over 4 on the one hand and ln 2 over 2 on the other. That has to be what happens. I'm not ready to give up yet. Our rewriting has got to be correct. It has got to be correct because the exponents have worked out. That can't have happened by chance. Have I messed up my logging? So I said that 2 cubed is bigger than 4, so I'm further from the max. So ln 2 cubed over 2 cubed, which is one side of my comparison, is definitely smaller than ln 4 over 4. Fine. And then I've tried to compare the cube root of 3 to 2. The cube root of 3 is obviously, I mean, without even doing this working, it's obviously way smaller than 2, which is smaller than e. So this is also further from the max, so it's smaller than ln 2 over 2. Yeah, maybe this idea just doesn't work. I've probably just done something stupid. Checking this law of exponent stuff again, just because it's such an easy thing to get wrong in principle. I don't see anything wrong with it. It's driving me mad. 2 cubed to the 3 to the third is 2 to the 3 times 3 to the third, which is 2 to the 3 to the 4 thirds. That's fine. Cube root 3 to the 8 is 3 to the 8 thirds, which is 3 to the third to the 2 cubed. So that is equivalent to that, is equivalent to that, is equivalent to that. No negative division, so that's fine. Two cubed is way further out than the max. It's also way further than x equals 4, for which we have ln 4 over 4 being the same as ln 2 over 2. Because it's further, it's smaller. So ln 2 cubed over 2 cubed is less than ln 4 over 4. The cube root of 3 is smaller than 2, which means that that's, yeah, it doesn't seem this line of attack works. So I think I'm going to throw in the towel there from exhaustion at 2 hours 32, and we'll see how this does in the marking. Okay, so after waiting, I've finally got my results. Obviously, I can't mark my own paper, so my colleague James, who is also a former STEP examiner, has kindly stepped in and graded my work. So let's go through and really just focus on where I lost marks. At least I'm hoping that there will be only a few, as opposed to looking at every mark I've gained. I think that should be a bit quicker. And we'll start from question 1. So, okay, we see already on the first page, something's gone a bit wrong. So in this graph, the 2 straight line segments that I drew were both really portions of the same line, y equals 2x. So that means that really they should obviously both be portions of the same line segment. Whereas actually, if I take the line drawn down there and I continue it on, it means that it should have been up there. So I've lost one of the G marks on this portion. This is the sort of thing that's very easy to get wrong in the exam if you're not careful, but it's the sort of thing that really you should be carefully going through and checking after completing your work. So, there'd be a bit of leeway, but this is a pretty big gap between what the graph is and where it should be. So, okay, 1 mark down. Let's see. Hopefully it's going to be plain sailing from here. So nothing wrong on the next page. Nothing wrong on the next page. This all looks fine. This looks fine. This looks fine. Okay, so I seem to be redeeming myself somewhat. That looks okay. Right, so I've lost another G mark for this plot. So what's actually happened here? Well, see, this is the sort of thing where if I'd just taken 20 seconds after completing the question to go back through and visually scan through what I've done, I'd easily have caught this, because I've just caught it from a visual scan now, even though it's been several days since I did the paper. I've obviously just made a silly transcription error. So the y coordinate was minus 10/3 root 5 over 6. And yet when I've copied onto the graph, I've dropped the root 5 over 6. So nothing mathematical or conceptual, just a silly mistake, a transcription error, copying my own work wrong. That's led me to get the wrong comparison for which turning point is higher or lower. So I've pretty needlessly dropped 2 marks on question 1. And why has that happened? Because I didn't go back and check my work. Ideally, it's good to take 30 seconds to a minute when you complete the question to just skim back through and catch any really obvious silly mistakes like this. And then obviously, if you have time at the end like I did, rather than collapsing from exhaustion from not having done many timed mocks recently, you would want to go back and do a bit more checking again. So bit of a disappointing 18, but nonetheless, not too bad. Hopefully, I'll still be on track for an S. What about question 2? Okay, so the first bits of question 2 looks completely fine. Still fine. Okay, so this seems to be going a bit better than question 1, at least so far. Yeah, okay, so this is the bit where I kind of gave up in practice. Right, so I was getting confused about failing to show that the real solution I was finding was valid. And because I had to make sure it was on the correct portion of the domain. And again, if I'd just taken, 30 seconds to come back to this at the end with a fresh pair of eyes, I would have realized my really silly mistake. I said here that if the right-hand side was negative, then I was done and the question was resolved. And I was then worrying about the case where it's positive. But it's always negative because we said b was greater than a half. So it's so easy to get this sort of tunnel vision when you're working on a part of a problem. You feel the clock ticking. In the real thing, it counts because it's going to determine whether you meet your university offer. For me, I know it counts because it's going to end up on YouTube. Under that pressure, it's so easy to miss the obvious. But if you come back to something with a fresh pair of eyes, it's easy to spot. So really, I could have just said, and it is, because B is already at least 1/2. So really my downfall there was the fact that I haven't been doing, obviously, regular 3-hour time mocks. There is a real stamina factor to step. And if I wasn't so tired at the end, I would have easily had time to come back and fix this. Okay, so yeah, I lost an E mark. Equally, I will say my exam technique of moving on was probably the right decision there. Because although it might at the time have felt like it could have been worth more, it was literally 1 mark I was stressing over, and it wasn't worth falling behind for. Okay, so subsequent workings, another silly mistake here. So when I cancelled that 4, in going from there to there, I've lost an X on that 4X. So just a silly mistake. Again, nothing more than copying my own workings wrong. Some people are really good at avoiding doing this. I've always been a bit of a clumsy mathematician. Now, that's not a problem. Clumsy mathematicians can do just fine on exams, but you need to have a checking protocol. I went charging in recklessly here without thinking about how I was going to check my work. I should have just visually scanned through, and I'm sure I would have seen that. So that's cost me another mark. I'm relieved at least there have been no big conceptual errors yet. It seems to be just silly mistakes. So another 18. Okay, could be better, but also could be worse. Let's see about question 5. So this is the integration that I was so pleased to see when it came up. So it looks like it's starting out fine. Okay, something funny's happened here. So what's obviously happened, even though up here I've said about the swapping of the limits, I've made a silly mistake here in that I haven't actually swapped the limits over. But I think in my mind, I had swapped them over, and hence I absorbed the minus sign into swapping them back. I've even written swap limits. So I obviously knew what I was meant to be doing, but I just wrote something wrong and didn't quite clock that I was carrying that wrong thing through line to line. Again, right, this would have been so easy to catch if I'd implemented the most basic checking protocol. At the end of the question or at the end of the part, just take 10 seconds to read back through what you've done. So I've no one but myself to blame for this. Another silly mistake mark lost. Okay, what about subsequent workings? So this looks okay. Oh no, another A mark. What's happened this time? So I've obviously dropped a 2, and therefore I've wrongly convinced myself that what I called case A works. In fact, because of that silly mistake there, that P should have had a 2 on it, so it shouldn't have worked. So I would have had to actually use case B. So another transcription error, another silly algebra mistake that I could have caught if I'd just taken the time to check. So how much damage has that done? I think just an A mark. Okay. And then part 4 looks all right. Yeah, so, okay, I've made another silly algebra mistake here, I guess going from page to page when I went from that to that. Ridiculously, I think I didn't reciprocate the 1 over k when I tried to reciprocate both sides. So yet again, a silly, clumsy mistake that I could have caught on a check. But I've actually not lost a mark because it says that implicit is permitted. So it looks like I didn't actually need to make P the subject. It was enough to give the implicit equations that I'd put on the page. And there is a principle in step marking called ignore subsequent working, where if you do meet the conditions for a mark, as long as you don't then subsequently contradict yourself, but you just make a silly algebra mistake doing something else that's not necessary, you normally won't be penalised. So that was close, but luckily for me, I didn't lose another mark there. 18 again. This is, I hope it's not going to be a clean sweep of 6 18s. This is getting a bit ridiculous. Okay, let's see the next question. So the next one was the differential equations. So I liked this question. I think this and the integration question really saved the mock for me in many ways because they let me get so ahead on timing when I had previously fallen a little bit behind where I wanted to be on question 1. So it looks like it's starting out fine. Got an ISW there, so I guess that expression for x was fine. When I chose to eliminate the nested fractions, which is a good habit, but not vital in this question, I obviously should have had an A there from multiplying through. So yet again, just a silly, clumsy algebra mistake. I could have caught it if I was more careful, if I was used to doing timed mocks and trying to check carefully as I go, or if I'd just done a scan through at the end, but I've not lost a mark because that form would have been accepted. So, okay, a lucky getaway there. So still on full marks on this question so far. I've got a BOD there, which means benefit of the doubt. I've not lost a mark, but there's something that's not ideal that they're literally giving me the benefit of the doubt on. And it's that my A has somehow turned into a Q as I've gone. Now, why have I not lost a mark for that? Well, I guess because there is no Q in this part of the problem. Although there is a Q in the next part, and maybe in the back of my mind I'd seen that on the page, there was no Q for this section. So, and you can also literally see my handwriting mutate, right? You can see the evolution of the A into a Q in real time. So there's no doubt what I intended here. There's no ambiguity. So I got away with it. Okay, lucky me. That was fine. That was fine. That was fine. Lost a mark here for not being careful with the modulus. So yeah, I was a victim of my own overconfidence here. So I think I said something at the time, like they're normally really sloppy on step mark schemes about moduluses. They normally in the mark scheme just have them vanish without justification. So I thought I'd be lazy to try and get ahead. What I should have done really is rather than that, put the A there, and then I could have just commented that the modulus was being absorbed into the constant. So obviously this was an unusual question and that the mark scheme was a bit more prescriptive there. Needlessly lost another mark. Okay, here it looks like I put the X twice, but then I've recovered on the next line. So yeah, the idea of a recovered slip is if you have made a kind of transcription error, but then you've corrected it yourself on the next line and it's not caused anything to go wrong subsequently, you may not be penalized. So another silly mistake there, but no mark lost. And it looks like the rest was okay. So I finally broken past the 18 barrier with 19, but really that should have been a 20, right? It would have been so easy to handle that modulus carefully. I just got sloppy and overconfident based on what the previous mark schemes have done. But just because the mark schemes aren't cautious about something doesn't mean a future mark scheme won't be. It's always best to prioritize, mathematical correctness and clarity. Okay, what about 11? So I liked this one too. This was the stats question. I know I corrected an algebra mistake as I was going, but I felt like this one I was able to see what to do quite quickly. And because it was a little bit conceptual, spotting how to organize the probability calculations, the algebra wasn't too bad. It's always nice to get some stats in the mix as well, just because when the stats is easy, it can be really easy. So I think I felt at the time I was on track for full marks here. Let's see. It was nice because there were lots of sanity checks, both things I could do mentally to see if my answer made sense, but also things where the question actually, had to show that, and it was easy to see if something had gone wrong. So I've got a mark here for implicit. So I guess that means I was meant to explain a bit more why that was the right thing to do, but it's implicit in what I've actually written that I've clearly understood what the explain mark was for. So this is very common. If an E mark says you got to spell something out and the student's not spelled it out, but has clearly and unambiguously used it, provided it's not a sort of missing justification, the E mark is generally awarded. Okay, so I'm still on full marks on this question. Still. Okay. And this last bit was a show that. Oh no! I've lost an E mark at the end. So I've got another 19. The question said, show that Zen wins a little over 35% more. I've just shown that it was about 35% and stopped there. If I just said that E was slightly bigger than 2.7, then I would have been fine. So that's a matter of just reading the question carefully. With a show that, it's so easy to get carried away when you've got the correct answer that you're looking for, and therefore, overlook the fact that they've asked for something slightly more specific. So really silly mistake there, but at least I got 19 this time and not 18. And then there was just question 3, which I came back to. So yeah, this is the one where I gave up at the end. I should have still had energy to keep going at the 2 hours 30 mark. I know you taking step for real now have youth on your side relative to I do, but doing maths for 3 hours should not be a problem. It's just the fact that I haven't sat down and done a step timed mock where I know that there's real pressure in such a long time. And it does take regular practice at this to build and keep stamina. So if I was practicing properly, I think in that 30 minutes that remained, I probably could have gotten that last bit out. In fact, I think I realized subconsciously after we stopped taking it what the resolution was. But let's see how much it cost me. So it looks like the first bits were okay. That's okay. Okay. Something's gone wrong with this graph. So I literally said that it was the translation of the other graph, yet for some reason I've had that going down rather than like that. So it looks like I've been awarded the method mark, but I assume there'll be a deducted accuracy mark later. Yeah, okay. So I think, you know, two things. Check your work. Essential to do that, because if I'd just taken 2 seconds to glance at what I've drawn, I'd have seen that error. And also, to be honest, I think by this point, my tiredness was starting to kick in. It's so important that you are doing mocks to build that stamina. So I lost a mark there, and then I know I'll have lost some at the end because I didn't finish. Yeah, so I was doing the right sorts of things here. I think essentially what I should have done is written it as something like 3 to the 4/3 squared rather than that, and then it would have worked. So this occurred to me straight after, but I'd given up, and so I wasn't getting anywhere with the way I'd identified those numbers. So I think this is the only part of the question which really got the better of me. I like to think if I'd taken that extra half an hour, even if I did still have the pressure, I would have gotten it right. But yeah, I think those 3 lost marks were fully deserved. So 108, not too bad. Comfortably above the S boundary. I think that's a couple of marks lower than the highest student got for real. So I'm a bit disappointed with that, to be honest, but it's not a disaster. But what I would emphasize is really there is no reason that this shouldn't have been at least 117. If I had just taken a moment to check my work, pretty much every drop mark would have been very easy to address. So there's a real lesson there. On one hand, that wasn't too bad. I was very comfortably above the boundary for an S, and I pretty much got the maths done in every question. That being said, there is absolutely no excuse for me not to be getting 120 out of 120. I have 2 maths degrees from Cambridge. I work as a research mathematician doing maths for hours day to day. I'm a specialist STEP tutor who has written solutions for every STEP question back to 2008. And at this time of year, I discuss STEP with my students pretty much every day. The lesson is that it doesn't matter how good at solving STEP questions you are if you aren't also reflecting on your exam technique. I went into this completely unprepared and without thinking about what I was going to do. So my exam technique was atrocious. I didn't pause to check my work. I didn't go back to look over things at the end. And more importantly, because I hadn't been practicing timed mocks under pressure, my stamina was pretty embarrassing. I should have been wide awake and breezing through at the 3-hour mark, as I'm sure you all will be doing regular timed mocks, but it takes practice to build this stamina. So don't do what I did. Make sure you check your work, and I'm sure you can do even better than I did here. If you enjoyed this video, stay tuned for my redemption arc. As the 2026 papers release, I'm going to repeat those in timed mock conditions, having taken some time first to warm up with other timed mocks and reflect on my exam technique. Fingers crossed we'll get a little bit closer to 120 that time. Thanks for watching if you made it this far. If you've had a go at this paper, let me know how you got on in the comments. And if you'd like to see more videos relating to STEP and other admissions tests, including my attempt at the 2026 papers when they come around, do remember to subscribe. Best of luck to everybody taking STEP this year. I'm sure you'll do fantastically.